talk about large-scale structure networks, which I'm interested in. A lot of people have talked about this, but I'm interested in getting away from the things that other people have talked about, community structure, stuff like that, and addressing other questions. Sure. Thank you. If you go to talks about networks, they show you pictures like this one here of the internet, beautiful picture of the internet, or this picture of a power grid, or this is a picture of a food web. This is a picture from my own research of a collaboration pattern between scientists. These pictures are very pretty, but they're kind of misleading in a way because they've been cherry-picked to be nice examples where you can make a pretty picture and you can see what's going on, right? They're relatively sparse networks with not too many nodes, and you can lay them out in some nice way, and you sort of really feel like you can see what the structure is in a network like this. And the trouble is that actually most networks that we look at really aren't like that at all. Most networks are more like this. Here's a picture of a protein interaction network. It's much denser. Not like it doesn't have that many nodes, but it's much denser. It has a lot of edges. It's very difficult to see what's going on. It's difficult to make any picture of this network. You just get this sort of hairball. Or this here, this is a picture of a metabolic interaction network. Or this is a picture of a portion of the World Wide Web. This is another protein interaction network. I have difficulty understanding why they even bothered to publish a picture like this at all. And what are you supposed to learn by looking at this picture, right? I can't get anything out of a picture like that. So, a large part of what we do is trying to answer the question, what do these networks look like when we can't actually look at them? It's simply not possible to make a reasonable visualization of them on a piece of paper. Good? Okay. So a lot of the work that people have done on network structure is to do with quantifying what the structure is in some more rigorous way. There's really two broad classes of techniques that people have used to do that. Small scale ones, which concentrate on things like degrees and degree distributions, correlations, clustering coefficients, stuff like that. And large scale structure in networks, which has primarily to date concentrated on community structure, which means division of networks into clumps of nodes. How can I partition the network into some useful division of the nodes? But there are other kinds of large-scale structure as well that are interesting, like core-periphery structure, ranking, latent-space structure, and so forth, and some of these that I want to talk about today. So there are many methods for quantifying large-scale structure in networks, but I'm particularly interested myself in my own research in inference methods and spectral methods, and it's primarily the inference I'll be talking about today because this is a program on statistics of networks. Seems appropriate. So what I want to do is first talk about community structure in networks, the archetypal form of large-scale structure, which may seem a bit silly because that's kind of what I'm trying to get away from in this talk. I want to talk about other things, but I think it's a useful starting point to sort of illustrate the kind of ideas, and then we can start to move away from it. So by community structure, I just mean stuff like this. In networks, I mean networks divide into clumps of nodes. There's a dense clump here and a dense clump here, and there are only sparse connections between them. So this is the kind of structure that occurs in many networks, and there are many examples where the clumps in networks have been shown to correspond to functional units in networks. It's also a good way of breaking down very large networks into smaller pieces that one can then analyze more reasonably. So it's become one of the most popular ways of analyzing large network data sets. In some cases, it's sort of obvious when you look at a network that it has community structure in it. This is a picture of a friendship network amongst school children in a US school. And it's very obviously for big groups in this network. But a much more common situation, as I kind of just said, is that you get something like this and you can't tell what's going on. It's just too much of a mess. There might be some clumps in this network that I can't tell just by looking at the picture. So we want some automated way of doing it. And from the statistical inference point of view, the classic way of doing that is to use block models. So I realize that this is familiar material to a lot of the people here. I will go through this quite quickly. What you do is you define a model of the kind of structure that you're interested in probing in the network, and then you fit that model to the observed network, typically using maximum likelihood methods. So in this case of community structure, we want a model that generates a network that has communities in it. So the stochastic block model does that by taking some number n of nodes, dividing them up into some number of groups, 3 in this particular picture here, and then placing edges independently at random between them with probabilities that depend only on which groups nodes belong to. So there's some probability, which I've denoted omega 1, 1 here, for instance, which is the probability of an edge between 2 nodes in group 1. Omega 3, 1, 3 is the probability of an edge between 2 nodes, one in group 1 and one in group 3, and so forth. So there's some matrix of these probabilities over there. So now what I'm going to do is take this model and sort of use it in reverse, fit it to the data, and extract the values of the parameters. The parameters of this model are these probabilities, omega, this matrix of probabilities that tells you the probabilities for the edges, but there's also another hidden set of parameters here, which are which node belongs to which group, and actually that's really the parameters we're interested in, because if I can tell you which node belongs to which group, then I've divided the network up into groups, and that's the goal here, to find the groups. So the parameters are these probabilities omega and the group memberships, which I'll denote G sub I. So G sub I will be the group that node I belongs to. So G sub I for this node here would be 1, and G sub I for this node here would be 3, and so forth. Just the label of the group that it belongs to.
I have one question about this setup. So first, you motivated that we have this community structure, you basically algorithmic applications, useful to have this representation. Now here the goal is you want to say that this block model should sort of approximate the network that you see when you only work on that, or what's the...
Right, so what you're going to do is you're going to say, so I'm going to fit the model to the data. So, you know, like the way I fit a straight line through a set of data points, right? So I have some bunch of points, they don't exactly fit a straight line, but I'm going to put a straight line through them. That's a useful thing to do because it sort of tells me the slope of my points and so forth. So I'm going to fit this model to the data. So, you know, a model is something where if I ran it in the forward direction, it would generate a network, right? I'm going to fit this model to the data in the same way that I fit a straight line through the points, and the parameters of that fit, the slope of the line, are going to tell me something interesting about my data. Now, just like the slope of the line, there is no claim here that it's going to be an exact fit, right? The data points are some scatter, and the line doesn't exactly go through them. I don't expect this model to be an exact fit for the data, but the analogy is a good one, that the parameters of the fit are going to tell me something interesting about the data. And in this particular case, it's really these parameters, the group memberships, which are the ones I'm interested in. So what I'm going to do, in fact, is I'm going to write down a likelihood function which says what's the probability that my observed network was generated by this model, and then I'm going to maximize that with respect to the parameters to find which values of the parameters are most likely given the observed network data. So this is a fairly standard thing. Before I get on to doing that, though, here's a really important mathematical aside, which I think is insufficiently emphasized in the literature. This may be familiar stuff to you folks, but I think this is important and insufficiently emphasized elsewhere. All of the networks that we look at are sparse, by which I mean that most possible edges that could occur in these networks are non-edges. If I choose 2 nodes at random, then with probability approaching 1 and the limit of large size, there is not an edge there. If I look at the adjacency matrix, almost every element of it is 0. Another way of saying that is that the number of edges in the network is little o of n squared. It goes up slower than n squared. There are n squared elements that I could fill in the adjacency matrix, but only a vanishing fraction of them are non-zero. An equivalent way of saying that is that the mean degree of a node in the network, the number of connections a node has, it can be going up, but it's going up slower than linearly in the size of the network. So double the size of the network, mean degree less than double, so it's little o of n. So that's what we call sparse network. The alternative to sparse network is dense network, which is one where the number of edges goes as n squared, and the average degree is increasing linearly in the size of the network. And that's sort of the classic distinction that a graph theorist would make between sparse and dense. But it turns out that that's not the important distinction. As far as we're concerned, the important distinction is another one. So basically, every network we look at is sparse. So the distinction between dense and sparse just doesn't matter because you never see dense. What does matter is the distinction between sparse and what I will call extremely sparse. I don't know that it really has a name, but I've seen it in some of your papers, for example. It's called extremely sparse.
Maybe, but I think usually I would just call that sparse, and your sparse would I call something intermediate. So I think vocabulary is not fixed here. One should be careful.
Fair enough. Okay, so for the purpose of this talk, I will call it extremely sparse, but I accept that this is not standard vocabulary. So by sparse, I mean that the average degree can increase, but doesn't increase as fast as n. By extremely sparse, I mean that the average degree is constant in the limit of large size. And this is a crucial distinction because how do I know about nodes in a network? What distinguishes two different nodes in a network? The only thing that distinguishes two different nodes in a network, if all you give me is the topology, is what their connections are, what other nodes they're connected to. That's the only thing that sets two different nodes apart. So you can think of the connections that a node has, the edges impinging on it, as being the data that you have about that node. And in this sparse case, where the average degree is allowed to increase without bound as n becomes large, you get an infinite amount of data about every node. And so you should not be surprised to learn that you can then do good inference on that node. You can learn things about that node with arbitrary precision. It's just like if I measure the same quantity an infinite number of times, I can get the statistical error down to 0. Right? I'm saying I have an infinite amount of data about each node, so I can do good inference on it. But in this case, where the average degree stays constant in the limit of large size, I just have a fixed amount of data about each node, and that means that there will be an error on my conclusions, no matter how large the network gets. So there's a crucial difference between these two cases, in that one case I expect to be able to do consistent inference, in the other case I don't. That doesn't mean that inference is not useful in this extremely sparse case. It just means that what I'm going to end up with is some posterior distribution over conclusions about my nodes, not a single maximum likelihood conclusion. So in other words, in the sparse case, simple maximum likelihood methods are expected to work and just fit my model to the data in the limit of large size. The likelihood peak is going to become infinitely narrow, and the single maximum likelihood conclusion is the one that is going to be correct. It's going to be consistent in the limit. In the extremely sparse case, it doesn't matter how large my graph gets. I'm never going to get that. There's always going to be some error in my conclusion.
So you're never interested in a random vertex? I was interested in every vertex?
In this particular setting, yes, I'm interested in every vertex. I'd like to be able to divide all of the vertices of the network into their appropriate groups. But I'm guaranteed to get some of them wrong in this extremely sparse case. It's always going to happen.
And you mean you expect to get some fixed, hopefully small proportion of them wrong. So even if you take a random vertex, it will be wrong with some probability.
Well, that's right. Exactly. Yep. So if I was looking at the sparse but not extremely sparse case, I can write down a likelihood function here that says the probability of an observed graph given these parameters omega and these other parameters g, the group memberships and the probability parameters. I'm using a Poisson form for the probability of edges here. You can use a Bernoulli form if you prefer it. It doesn't matter. They give essentially the same results. This one's just a little technically easier to do. I want to maximize that thing. Typically, I actually maximize its logarithm. Don't really care. Here's the logarithm. It simplifies in a nice way. So this is just the logarithm of that expression here, but I've collected terms. M sub rs in this expression here is the number of edges that run between group R and group S. You give me two groups, count the number of edges that run between them. N sub R and N sub S are the number of nodes in group R and group S. Right? So the setup here is you give me a network, you give me a candidate division of this network into groups. For that candidate division, I can calculate how many nodes there are in each group, how many edges run between each pair of groups. I can plug those numbers in here. It gives me the value of the log likelihood. And that's the thing that I want to maximize. I want to maximize it with respect to two things, the parameters omega and the parameters g. I'm going to do omega first because it's easier. I just differentiate with respect to omega in this expression. And I'll find that the optimal value of omega is this thing here, mrs over nr/ns. Substitute that back into here again, and I get something called the profile likelihood. This is the value of the log likelihood at the maximum with respect to omega. So I've removed omega from the problem now. I've already done that maximization. All that's left is to maximize with respect to who's in which group. And that's, of course, the interesting thing. I mean, that's what we care about here. So now the claim is that if I'm in the sparse but not extremely sparse case, then in the limit of large n, I should be able to do this consistently. If I just maximize this over all possible assignments of nodes to groups, I should get a consistent answer. Meaning, if I took a network that really is generated by the stochastic block model, and I fed it through this mechanism, out would come at the other end the true assignments of nodes to groups that I used to generate that network in the first place. And this consistency was proved rigorously by Peter Bickel and Ayu Chen in this paper in 2009. Peter Bickel, of course, who was a visitor here in this program until just a couple of weeks ago. So this works nicely, but this is specifically for the sparse, not extremely sparse case, right? It's not entirely trivial to do this last optimization stage over all possible assignments of nodes to groups, because there's an exponentially large number of assignments of nodes to groups, and that takes a while to do, but there's various heuristics that give pretty good results. So people actually do this, and it works well, provided your network is not too sparse. If you're in the extremely sparse case, however, now you have a problem. So in the extremely sparse case, well, so with the probability parameters, the control probability of the edges, you're still okay, because there's just a fixed number of those, right? There's this fixed matrix of probability parameters. So in the limit where the graph becomes very large, you have an arbitrary amount of data telling you about a fixed number of parameters. So again, you expect the simple maximum likelihood will give you a nice narrow likelihood peak, and you'll be able to infer the values of those parameters very accurately.
Sorry, are we going to come soon to the number of groups being variable changes?
At the moment, let's say the number of groups is fixed. Number of groups is fixed as the graph becomes large. That's a perfectly reasonable question. There's a whole bunch of interesting things going on there, but we can talk about that later if you like.
Yeah.
For the moment, I'm assuming the number of groups is fixed, so the number of omegas is fixed, and so you can do good inference on them. Simple maximum likelihood will work. The problem is with the group memberships, there's one of those for every node, and so the number of parameters you're trying to infer is going up as fast as the amount of data you got, and as we've said, that means that you expect there to be some error in your inference, no matter how large the graph gets, or to say that another way, there is some posterior, non-trivial posterior distribution over possible group assignments. It doesn't become narrowly peaked. So this gives you a sort of strange asymmetric situation.
There's another problem as well, right? Most of the data,
possibly many.
Most of the network that you get from data don't look like a stochastic block model.
Oh, well, so fair enough.
That's a pretty serious
So all models are wrong, but some models are useful. Right, yes.
Okay.
So absolutely, I don't actually believe that any of these real networks are generated from a stochastic block model. Moreover, there are important additions to the stochastic block model I can do, like degree correction, for instance, that I haven't addressed here. We can certainly talk about that, but I'm sort of regarding that as, I don't really want to talk about community detection, right? So that's a technical detail that's important if you really want to do this, but I'm not going to talk about it here.
So another issue is that you've got sort of order n squared nuisance parameters with order n parameters that you're interested in, if you regard the probabilities as nuisance parameters.
So the probabilities, I'm actually going to say that there's a fixed number of groups, so there's order a constant of those probability parameters as n becomes large. Right, and so in that regime, I believe that I can infer the omegas exactly. Right. So I end up with sort of, yes.
One more question with the setup. So are you actually interested really to find for each vertex the membership, or just want to know the distribution? So what kind of questions?
Well, exactly. So I mean, I can't know the membership. I could, in principle, calculate the maximum likelihood ones, but it's not going.
For example, 30% are in this one group and 20% in the other group. So I'm asking, so what kind of questions do you want to answer?
So in this particular case, what I want to answer is who belongs to which group. That's not the only question that's interesting, but let's say that's the question I want to answer. I can't actually answer that question. I can only answer it probabilistically. There's some posterior distribution over group assignments. So I can get the omegas exactly, but I need to calculate a complete posterior over the group assignment. So I have this slightly odd asymmetric case, but there's a standard method for dealing with exactly this asymmetric case, namely the so-called expectation maximization algorithm, or EM algorithm, which works very beautifully in this case. You can look at this various different ways. I'm a physicist, so I look at it in terms of the maximization of something called free energy, which is, so define Q of G to be this unknown posterior distribution over group assignments. So this is a probability distribution over possible assignments G. The free energy is the average over that distribution of the log likelihood. There's the log likelihood from the previous slide, plus the entropy of the posterior distribution. So minus sum over G Q log Q is plus the entropy of the group assignment, the posterior distribution of group assignments. So this thing here is what I, as a physicist, will call free energy. It's got an energy term, it's got an entropy term. And if you just simply maximize this thing jointly with respect to the parameters omega and the posterior distribution, with respect to the complete distribution, not with respect to the group assignment, then this should give you the thing that you're looking for. Turns out you can do that. You can write down the equations. Here they are. Here's the equation for what the omega should be. Here's the equation for what the posterior distribution should be. So the way this works in practice is this equation gives you what the parameters should be if you knew what the posterior distribution of group assignments was. And this equation gives you the distribution of group assignments if you knew what the parameters omega were. So what you want to do is simultaneously solve these two sets of equations for everything, and the traditional way of doing that is just to, it's a very stupid way of doing it, it's just you guess a value of q, you stick it in here, that gives you an omega, you put that omega in here, that gives you a q, and you just keep on going back and forth between these two equations, the thing converges. That's the so-called EM algorithm, and it works very nicely in this particular case. Just for fun, I thought I would give you one application. So people really do this in practice. It really works, and it gives you useful information. Here's a sort of fun application from a paper that I did recently with a sociologist at Michigan called Elizabeth Brooke. This is an application to a dating network. So this is dating as in, American slang for going out with someone. It's data on who goes out with who. So what we have is data on 4 million users of a large US online dating network. This is one of these places where people go and post pictures of themselves and description of themselves and so forth, and you can browse other people's pictures, and then if you see someone who looks interesting, you can send them a message. Right? So what we have here is we have basic demographic data on these 4 million users, like age and race and location and so forth. And crucially, we have the messaging patterns. We know who sent a message to whom and when. So that's the network. That's where the network comes in, right? It's the messages being passed between the users of this site. So we did community detection on this thing. We constructed networks where the messages are the edges. Actually, technically what we did is there are edges when people exchange messages in both directions. There's an awful lot of messages on these websites, it turns out, that only go one way. Somebody sends a message saying, hey, and the other person just completely ignores them. So you throw those out, right? That's like 80% of the messages on your website is just completely ignored, right? So we figured it's only real actual contact between people if the person replies, at least once, right? Okay, so those are the messages we looked at, yeah.
Do you have missingness in the covariance?
Sorry?
Do you have missingness in the covariance?
Yes, we do. Lots of missing stuff, yes.
Once is enough.
Yes, right, once is enough, right? There has to be at least one message in each direction between a pair of people for there to be an edge.
You don't take the multiplicity into account.
We do not.
Because that
No.
could actually be very important.
There could be interesting information there, absolutely. At the moment, we're not taking that into account.
Certainly, if you put Poisson variables on the edges, which is basically what you're doing, right? You could take that into account.
Yeah, you could. I don't know if it's Poisson. A number of other studies have shown that it's actually sort of strongly non-Poisson. Conversations tend to be either very short or very long. But certainly one could look at that. I'm sure there's interesting stuff there. Actually, once you have a data set like this, there's so much interesting stuff there. It's amazing. So we've only scratched the surface. But so what we did was we constructed these networks, 4 million people. Obvious point that I should point out is that because we're looking at people who self-report that they are interested in members of the opposite sex. So that means that almost all messages are going between a man and a woman or a woman and a man. Right? So there's an obvious sort of bipartite structure in this network that's divided into women and men, and all the messages go in between them. But on top of that, it turns out there's also other structure, group structure, like there's group 1 here and messages within group 1, and group 2 here and messages within group 2, but very few messages going between groups. That's really the structure we're interested in, right? The division between men and women we could have gotten by other much simpler methods, but this division into groups is what we're really looking at. And the block model is very nice because it captures both of those things automatically. Right? It can spot the division into men and women automatically. You don't have to tell it about that. You can also spot these other divisions as well. So if you actually look at the matrix of omega values, here's a division into 8 groups of one of these networks. And what you see is this sort of off-diagonal thing. Here's all the messages off the diagonal. So 4 groups of men, 4 groups of women in this particular division. And all of the probability is in the off-diagonal blocks because it's between men and women. But it's really the structure within these blocks that we're interested in. That's what we want to look at here. So here's just a few things that we found. One maybe sort of obvious result is that a lot of the community structure in these networks is driven by age. Right? So here's results for 4 different US cities that we looked at: New York, Boston, Chicago, Seattle. And in each case, we found a group of men and women there, lower 20s, upper 20s, 30s, and then 40s and above. And it's not exactly the same across cities, but it's obviously fairly constant behavior. Within each group, the men tend to be a little bit older than the women, not very much, like a year and a half, something like that, but it is significant. We see it there. So this is not surprising, right? I mean, it's sort of obvious that young people go out with young people and old people go out with older people. So we shouldn't be surprised to see age as being an important variable dictating the group structure in this network. But there are other things going on as well. For instance, this is a plot of the sex ratios within the groups. And here there's an interesting pattern in all of these 4 cities and everywhere we looked at. The younger groups, these are numbered in order of age, the younger groups tend to have more men than women in, and the older groups tend to have more women than men in. So if you look at the blue is going down and the red is going up. Right? And it's the same across all of these. Okay? So it's not exactly the same, but the pattern is the same. So we don't know why this is, right? Because we don't have any information about motivation here. All we have is what actually happened. But you can speculate about some of the things that are happening here. So one thing that happens here certainly is that women on average get married younger than men in the US, and that takes more women than men out of the younger dating pools. So there just tend to be fewer women, period. So that's one thing that will drive the bottom end here. Another thing is that women tend to live longer than men. So if you look in the older dating pools, there are more women than there are men because some of the men have died.
But you only went up to age 60 on the previous one.
That's true, although, I mean, it's certainly true in the 50s and 60s that more men than women are dying. It's absolutely true by a long way. Yeah, absolutely. Yes.
Also, isn't it, or am I making a mistake, isn't it true that since the women in the 60s, they may have been married to men who were 70 and then died?
Fair enough, yeah, indeed. But another thing that might be happening here, and again, this is still speculation, is that within our culture, it is a lot more acceptable for women to date men who are older than them than men who are younger than them, and vice versa for the men. Right? So it may well be that there are some women who are sort of effectively dating an older dating pool because they're interested in dating older men, and there's some men who are effectively dating in a younger dating pool because they're interested in dating younger women. So there may be some sort of pressure pushing the men and the women sort of in opposite directions, just sort of a cultural pressure effectively going on here. Again, we don't know this for certain because we can't actually say what people's motivations are, but there's clearly a pattern going on.
Biological clock is not
Sorry?
involved? Biological clock?
Yeah, absolutely. I'm sure that plays a role.
35 and 45.
Yeah. Okay, so that's all about community structure. Fun. So what I want to do for the remainder of the time is talk about other things that are not community structure. Try and get away from that and see what other kinds of structure we can look at in networks. And what I'm going to do is I'm going to start off with some very sort of trivial variations of the community structure idea, and then sort of slowly get a bit further away from it as I go. So let's see what other kinds of things we can do with data. So the first one really is still community structure, but it's community structure in a different situation, the situation where the data that you have are uncertain. So this is something which I feel, another example of something which I feel hasn't been really very much emphasized in the statistical networks literature, is that presumably all of the data we have are inaccurate. All scientific data has errors in it, right? And almost all analyses that people do assume that the network you're given is actually the network. But this is probably not true, right? There's probably errors in there. Another way of saying that is that you're usually given sort of zeros and ones. There is an edge here, there isn't an edge here. But really those are uncertain. Maybe I'm only 75% certain that there is an edge here. Or maybe I'm 10% certain that there is an edge here, meaning that I'm 90% certain there is a non-edge there, right? So I'm going to generalize my 0, 1 adjacency matrix representation of the network, something I'll call Qij, which is a probability that there is an edge there. And it's something you can run all the way from 0 to 1. 0 and 1 correspond to the same things they've always corresponded to. Definitely not an edge, definitely an edge. But other things in between are certainly possible.
But you assume that your probabilities are certain.
So at the moment, yes. I'm going to assume that my probabilities are certain. Yes, I guess, indeed, one could take it a step further, but I'm not going to do that at the moment. Okay. So there's plenty of data out there that is like this. but it's not usually handled, I think, in a way that makes sense. So the typical way you handle data like this is to apply a threshold to it. You just say, well, everything that's over 50% probability, I'm going to call that an edge, and everything that's under 50% probability, I'm going to call that not an edge. Okay? So this has some obvious disadvantages. So it does turn it back into a nice binary network, and you can use whatever method you're familiar with now. But in the process, it throws away a lot of useful information. Right? There's an awful lot of difference between an edge that's 51% certain and an edge that's 99% certain, but a threshold at 50% will make no distinction between those. So call them both an edge. Right? So you've sort of thrown away a lot of information. More importantly, it fails to satisfy some really basic requirements that probabilities have. Right? So the so-called requirement of calibration, if I have 10 pairs of nodes, all of which have 90% probability of an edge, then in expectation, I expect 9 of them to be edges and 1 of them to be not an edge, right? That's a basic just definition of what probability means, but this kind of thresholded data fails to satisfy that very basic requirement of probability, right? That if you take those 10 edges and you threshold them at 50%, well, they're all 90%, so you'll get a 1 for each of them, and you'll call all of them edges. So in expectation, all 10 of them edges, not 9 out of 10 of them. So it just fails to satisfy basic probability requirements. So here's a better way of approaching it. I'm going to write down the probability that I got the observed data, this set of probabilities of edges, given the groups and given the unknown edge probabilities. In this form here, here's the thing I had before. The probability is the actual adjacency matrix, given the group memberships and the probabilities. So this is just your stochastic block model, although one can use other models here as well. But let's say this is a stochastic block model. And the trouble is that the actual adjacency matrix A is not a known thing. We don't observe that. What we observe is this Q thing. So that on top of this, there's some other process, or P of Q given A, which is the probability that you got some Q, the actually observed data, given that the true underlying network was this A thing which you don't observe, and then some overall A, you get P of Q. So this P of Q given A sort of represents a noise process of some kind. It's your true network getting messed up because there's experimental error in your data. And we don't know what this noise process is. We know what this bit is if we make an assumption that we're using a stochastic block model, but we don't know what this bit is here. The beautiful thing is it turns out you don't need to know what it is. If you require that your data satisfy this condition of calibration, that it satisfies the basic constraint of being a probability, then it turns out that you know what this thing is to within a multiplicative constant, and you don't care about a constant because I'm just going to do maximum likelihood. This thing doesn't change the position of the maximum. So it turns out that this thing here, the noise process, doesn't matter, and then you can write down an EM-style algorithm for this noisy model, similar to what we did before, and it works pretty well. This plot here shows, just for some synthetic data, you make up a network. The lower curve is what happens if you use the thresholding technique. You take a threshold and then you use some ordinary community detection method on it. How well that does depends on what threshold you choose, but even at its best point, somewhere around threshold equals 0.3, it comes nowhere close to the performance of the algorithm I just chose. The vertical axis here is fraction of nodes classified correctly, which I can calculate because I'm using some synthetic data where I generated the network and I know who's in which group. This thing on the right is an ROC curve. It's basically demonstrating the same thing, showing that you do a lot better than if you threshold the data. Okay, so that's one example of a little bit more sophisticated than the standard community detection thing. Let's move a little bit further away.
Where you have
Yeah.
data of this kind?
Sorry?
Are there examples where you have data of this kind?
Yeah, actually, there are plenty of examples, but a lot of biological data is like this. So, for example, protein interaction data is mostly of this kind. What you do is you do an experiment many times, and on some fraction of those times, you observe a connection between two nodes, and some fraction you don't.
And you can use that as an estimate.
Yeah, and then you use that as an estimate of your probability. So if you look at the string database, for example, which is the standard big protein interaction database, this is the form of the data.
Why can't you just use the weighted adjacency matrix?
So the models that we're talking about, so one could do that, but the models that we're talking about don't inherently generate weighted adjacency matrices. They generate unweighted ones, right? You have a Bernoulli or Poisson process, which is just saying, I have an edge here or I don't have an edge here, right? So in order to use weighted data, you would have to come up with a generative model that generates weights. And
this Q here can be treated as weighted adjacency matrix.
yes, you can treat it as a weighted adjacency matrix. The nice thing about this approach is that the equivalent thing, where you have to decide what's the process that generates the weights, is this P of Q given A, this thing here, which it turns out you don't need to know. You can make up a model that generates weighted networks, but in that case you have to make some assumption about what the process is that generates the weights. Right? So people have done things like that. Whether I agree with their particular assumptions, I don't know. But you have to put an additional assumption in.
So it's very nice. So it's connected. That term you have the P of Q given A.
Right.
That's connected with like all this literature of missing data mechanism, coarsening mechanism, and so on.
Right.
But the thing is like there's a whole literature that tells us when that mechanism is ignorable. This is when you can drop it from your likelihood. When it's going to cancel out. So the thing is like, I would say, I think there's the implicit assumption that that term has parameters, but those parameters have nothing to do with the parameters of the underlying network.
Ah, I see.
That's
Well, so
so-
yes, that's probably true. Yes, I agree. That the form of this does not, the form of this function, it depends on A, but the form of the function itself doesn't change when you change the underlying network. Yeah, I think that's probably fair.
Yeah, so there are general assumptions that tell us when you can drop the term.
Yep.
You have to keep
Okay. Very good. Okay, so here's getting a little bit further afield now. This is still kind of community structure, but I'm going to make it a little more general now and talk about community structure where the groups are allowed to overlap. Right? So instead of just dividing up into groups, I'm going to divide up into groups, and there's going to be some possibility that a node can belong to more than one group. Right? So in many cases where you might imagine this happens in networks, you know, if you think of a social network, then you can have connections in your family and connections amongst your university friends and connections amongst your co-workers and so forth. You belong to several different groups of friends, right? So it's not necessarily the case you belong to only one group. And we'd like to be able to see that kind of structure in appropriate networks. So one way of imagining you could do that is we could generalize the model to so previously we had these discrete parameters which said what group you're in. Now we could have some parameters which say sort of what fraction you belong to each group. You can imagine doing that. Instead of just being 0, 1, you're in this group or not, I can now be 50% in that group, 50% in that group. Turns out, actually, a nicer way of doing it is to introduce a set of parameters, I'm calling theta IR here, which are not exact, they're sort of like the fraction, but actually what they really are is sort of the degree for a node in a particular group. Basically, how many connections I have to nodes in that group and how many connections I have to nodes in that group, right? So it's an unbounded parameter, it's not a 0, 1 parameter, right? It turns out that math just works out nicer if you do it that way. Anyway, in that case, you can write down, again, a likelihood function. So the group memberships have now been replaced by these thetas, which sort of say the fraction by which you belong to any group. And you can write down an EM algorithm for the same thing as well. And one of the nice things about this is it turns out the EM algorithm can be written down in closed form. Previously, the E step of the EM algorithm, which gives you a posterior distribution, was a sum over an exponentially large number of states, which you have to do by Monte Carlo or something like that. Here, actually, it's just a sum over a polynomial set of states, which you can do in closed form. So this EM algorithm is actually, it really is just these 3 equations, and doing this calculation is like a little 5-line program which just goes around these 3 equations over and over again until they converge. So you can do this for very large networks, millions of nodes. And it gives things like this. So here's a little social network divided into 2 groups, and most nodes have been put in one group or the other group, but there are a few nodes down the middle here that have been split between groups. So this one here. So what it's doing is assigning most nodes just to a single group still, but some of them are split between groups. And it's interesting to note, actually, it tends to be the high degree nodes, the ones with lots of connections, that get split between groups, which sort of makes sense. High degree nodes are a bit of a problem for community detection algorithms, because if you really have lots of connections, then you probably have connections to many different groups, and then you don't sit comfortably anywhere. You're not just in one group. So it tends to be the high degree nodes that get placed in a mixture of groups. There's quite a few of those in the middle of the plot here. All right, let's take things a little bit further, and getting a little bit further away from community detection. Communities here were defined just by there are probabilities for connections within and between groups. Here's a more general idea of communities. In this idea, I'm going to say there's some number of groups, and this node here, its membership in group 1 over here is defined by the fact, for instance, that it has a whole bunch of connections to this group and a moderate number to this group and very few to that group and maybe a couple to its own group. Or any pattern you like, right? So its membership of group R is defined by probabilities of connection to every other node now. So I can have very general patterns of connection here defining membership in groups, not just probabilities of connection within and between groups. So you can do an EM algorithm for this as well. It also works out in closed form. Let me give you an example of the kind of thing that this can do. Here's just an artificial network that we made up to illustrate this one. So what this network is 4 groups of nodes around here, and these 8 keystone nodes in the middle. This was sort of inspired by food webs in ecology, which sometimes have structure like this. So what it is there's a lot of edges in this network, which we just threw down completely at random. They're intended to be distraction. We're trying to throw the algorithm off balance. And then there's a small fraction of edges. Each node is connected to 2 of these keystone nodes in the middle. And that's where all of the information lies. The only thing that distinguishes nodes, what groups nodes belong to, is who their leaders are. Right? That's the only signal in the network. Most of the edges in the network are just rubbish. So this is the sort of thing that absolutely cannot be detected by traditional community detection. In fact, this picture here you see is the division produced by a traditional community detection algorithm, and it's completely failed to group them properly. But if you run that other more general type of analysis that I just described, it gets most of them right. It's spotted that almost all of the nodes in the network, the edges in the network, are just rubbish, and it should ignore them, but there's a small fraction that really contain the information, and it's picked out which ones those are and correctly divided the network. So again, what it's doing is it's defining groups now by the pattern of connections to all other nodes in the network. And in this case, it's spotted that what that means is your connections to these 8 nodes in the middle are the informative ones, and all of the other ones don't matter. I was supposed to stop at 3 o'clock, but I got here late. Do you want me to finish the last 10 minutes or so? I got like 3 more examples. So, right. Okay.
We can always leave.
Okay. Sorry?
We can always leave.
Absolutely. Feel free to leave at any point. And again, I apologize for being late.
Can I slowly ask about this? So what does one actually now do? If you have this structure, so what does one actually now do with it?
Oh, well, I mean, obviously this is a synthetic example, so
Yeah,
it doesn't tell you.
so even with other examples, so suppose you now have this, so what kind of questions is one really interested in?
So what this allows you to do is, it allows you to do classification of nodes in networks, so divide them into groups, without sort of knowing what kind of structure you're looking for beforehand. Previously, we had rather specific constraints on the kind of structure we're looking for. Now there's a much larger vocabulary of structures that you can look for. So this method can find traditional community structure in networks, for instance, in this example here. It could also find all sorts of other structures,
Well, I mean, like,
and you don't need to know
But
what
if you
structure
know
it is.
this structure, what do you gain from it? Can you run algorithms better on it, or why do you want to?
Oh,
know
I
this
see.
structure?
So more generally, the whole point of doing this kind of stuff is that we sort of want to understand the makeup of a network. Yeah, so it's not about running algorithms on something, it's about data analysis. It's about, I measured a big biological network or something like that, and I believe that there is some simple way of describing this network, right? I can describe it by telling you where every edge is, but that's not a useful description. I believe that there's a simpler way of describing it, like in this case, by telling you that really all that's going on here is that there's a small number of leader nodes, and everything else is, as far as I can tell, just random. So what I'm looking for is compact ways of describing what's going on here. Why am I doing that? Well, it's because I believe that that will lead me to something about the function of this network, right? My ultimate goal is, I have a metabolic network or something and I want to understand its function. But it's this big, complicated thing and I don't see any hope of doing that. But if I can give you a compact description that says, really, this is all that's happening in this network, then the hope is that that will lead us to an understanding of the functioning of the system that's described by the network.
But
I can't guarantee that will happen, but that's that.
in this case, for a similar example, do you decide beforehand that you want to look for 4 groups, or does that come out as part of the algorithm?
In this case, you have to specify the number of groups. So the whole issue of choosing the number of groups is important one, a separate one. I can talk about that if you like. I wasn't planning to talk about it today, but there's certainly things that we can do there. The most
I guess the
successful.
obvious thing you can do is just run the algorithm 3, 4, 5 groups and so on, and look at the results. And
Well, yeah. So you might
I guess
think
you're
that.
more sophisticated.
Yeah. So the catch is that the likelihood always increases when you increase the size of your model.
Yes.
And so there's basically 2 classes of approach that one uses to get around that. One is sort of the analogy of so-called Wick's theorem in statistics, which says, okay, the likelihood increases when I increase the number of groups, but does it increase by enough to justify increasing the number of groups? In other words, if there really weren't, I do it for 4 groups and I do it for 5, if there really aren't 5 groups in the network, I still expect the likelihood to increase. If there's really only 4, I still expect to increase by some amount. So let's work out how big that amount is, and if the observed increase is no bigger than that, then I haven't found anything significant. So that's one standard approach. Unfortunately, there are technical problems with getting that to work in the network context, which are associated with the fact that these networks are sparse. Because they're sparse, it means that the parameters, the probability parameters, are very close to the 0 lower bound that they can have. And so the approximations that one uses to derive equivalence of Wick's theorem, which is basically Laplace's method, it's basically Gaussian approximations about the maximum, don't work because the Gaussians are sort of censored by the lower bound on the probability. So far, as far as I know, people haven't been able to get around those problems. In fact, even in much simpler settings, there are very basic statistics problems for which the equivalent result is not known. So the most successful techniques that people have used so far are Bayesian techniques, where you integrate out the probability parameters and you get a probability distribution over the group assignments only and the number of groups. And then you maximize that with respect to the number of groups. And now in that case, you don't expect the likelihood to increase without bound as you increase the number of groups. And those methods work apparently quite well. Sort of basic consistency tests are pretty successful. The catch is...
Don't they depend on what prior you choose to begin?
Well, yeah, also absolutely they depend on what prior you choose. So typically in order to get them to work, you need to assume a sparse prior. But there are also technical problems, the main one being that in order to sample from that posterior distribution of group assignments, the only way we know of doing it is Monte Carlo, which is pretty slow. So it limits you to fairly small networks.
So -2 log likelihood would not be chi-squared. So you don't have that distribution.
Yeah, exactly. So you mean in the frequentist version of this? Yeah, exactly. It's not chi-squared. So yeah, Wick's theorem would normally say it's chi-squared with a number of degrees of freedom equal to the number of probability parameters that you're trying to fit. And indeed, in this case, it's not quite chi-squared. And it's actually very obviously not chi-squared if you just do it numerically. It's very clear that it's not.
But you could try to do a goodness of fit test on top of the estimation.
You could do it numerically, and people have done this. For instance, there was a paper by Chris Moore a couple of years ago, and one of his students, they did this. So in other words, you just generate a lot of networks that have 4 groups, fit them to 5 groups, see what the increase in the likelihood is, and then calculate a p-value numerically from that distribution. So you can do it, but that's going to be even more work than doing the Bayesian Monte Carlo, because you have to do it many times. You have to do 1,000 networks or something like that. So in principle, it's doable. It's a lot of work numerically.
In statistics, often these problems are solved by some sort of penalization method, right?
Right. So that's effectively what the Bayesian version is doing. So if you're familiar with the derivation of the Bayesian information criterion, essentially what it is let's calculate the integrated likelihood, just integrate out the parameters, but you do it by using Laplace's method. So you do it by a Gaussian approximation about the maximum and just calculate the determinant of the Hessian around the maximum. So the thing is with these network models that in most cases you actually don't need to do that. People have done that. They've derived versions of the BIC for networks, but actually you don't need to do that. You can do the integrals in closed form for most of these models. So there's no need to make the Gaussian approximation. You can actually just calculate an explicit formula for the integrated likelihood and then sample from it. And that really works quite well. Okay, so just to go through a few more examples, I think I have 3 more examples. I think it's fun. I'll just mention this one very briefly. Core-periphery structure is now completely getting away from classifying things into groups. Core-periphery structure is, can I find sort of the core nodes in the network and then the sparser periphery around them? Again, I can do that with a stochastic block model or something like it, but now the parameter space is different. Now I have strong connections within one group, medium connections to the other group, and the weakest connections within the other group, that kind of thing. So instead of the probabilities being strong on the diagonal and weak off them, they just sort of get weaker and weaker down the diagonal. So it's still the same model, and you can still fit it in the same way. You're just looking for a different kind of structure.
Well, in this case, I guess that you typically would expect the core to be a rather small proportion, or is that wrong? So in cases where you want the core to be big?
So one could certainly do a cross-validation type thing, consistency test, where you generate from the block model a network with a core and a periphery of any size that you like.
Certainly.
Right.
But I was thinking, now, if you were really going to apply this to something real.
So yes, that's probably true. So real networks sort of famously have these highly skewed degree distributions where you have a small number of high degree nodes and a large number of low degree nodes. And so I think, yeah, you're probably right.
And I also think if you have a real network where really the core isn't that well defined, if it's going to make sense to talk about the core, it ought to be rather, at least not very well defined boundaries, but at least it should be some rather small set of rather high density, as you say, with a very skewed distribution.
Right.
Otherwise, it seems that you're looking for wrong kind of structure.
Right. I think that's probably exactly right. That's certainly what happened in this. This is a picture of the internet run through one of these methods.
So I mean that means that it is mathematically the same, but still we have a somewhat different situation than the previous one. We look for communities which presumably are more or less comparable in size.
Right. Absolutely. I agree. And one of the interesting things about this is, since you're fitting the same model, it's sort of agnostic about what structure you're going to find. In some networks you'll find community structure, in some networks you'll find core-periphery structure, and you don't get to choose that unless you put constraints on your parameters. The model just sort of says whatever's the best fit. And in some cases you get one, in some cases you get another.
So is this very much different from just selecting the highest degree versus the core?
It turns out to be not very much different in many cases. Yeah, you're absolutely right. But to be fair, often the interesting nodes are the ones for which that pattern doesn't hold. So some small fraction of nodes that are not in the group you would expect them to be in based on their degree alone. And often those are the ones that you want to focus on. It tells you that there's something interesting going on. This is some work we did on sort of hierarchical decompositions of networks, where networks divide into groups, and then the groups divide into 4 smaller groups, and they divide into smaller groups, and so forth. This is kind of structure that you certainly do see in real networks. The way we did this was we fitted it with a tree. So we're representing the hierarchy by a tree. The top node in the tree represents the whole network. It splits into 2, those split into 2, and you keep on going down until at the lowest level of the network you just have single nodes. So the tree here is playing the role of the community division in standard community detection. And then we place probabilities on all the internal nodes of the tree, such that the probability on, say, this node governs the probability of an edge between any 2 nodes down here that have that as their lowest common ancestor. Right? So lowest common ancestors in the tree have probabilities on them that tell you what's the probability of an edge in the network itself. So the tree is not observed. It plays the role of the hidden group memberships. Only the nodes along the bottom are observed, and the connections between them in the observed network. So you can do similar kinds of maximum likelihood things here. It's a little bit more dicey because one of your variables is a tree now. Previously it was just a set of numbers. Now it's a tree, so you have to do Monte Carlo simulations over trees, but there are well-established ways of doing that. It can be done, and you can take networks, you can find the best tree that shows the hierarchical decomposition of that network, or you can just draw a picture of it like this, which sort of divides it into boxes, and then the boxes into boxes, and so forth.
So again, I guess that you choose the size of the tree something in the beginning, because if you allow large trees, there are very many trees.
So in this case, we used a binary tree, in which case...
But so don't you want to, or do you want to have it so that, okay, so you want to have something like log n steps so that each
So in general, there'll be log n steps. We go all the way down to the bottom of the tree, right? So yeah, there are many possible trees, but we consider trees that go all the way down. So this is actually an ecological network. It shows a network of hosts and parasites. So there's some interesting things like this over here is a host and its collection of parasites, and they've all been put in one group. But at the next level down, the parasites have been broken off on their own and put in a separate group. So the algorithm is both recognizing that the host and parasites together form a unit, an ecological unit, but that the parasites have more in common with each other than they do with their host, right? And that's even though there are no edges between the parasites. The only thing that makes the parasites common to one another is the fact that they have the same host. So it can spot kinds of structure like that. This can do a bunch of other things. We use this model, for instance, to do link prediction in networks. So you can ask within the model, what are the most likely edges to appear in the network? And some of those edges may not actually be there in the observed network. In that case, we say, that's suspicious. I expect there to be an edge here, but I don't observe one in the network. I'm going to predict that that edge is missing from my data. So you can do tricks like that to predict missing data in networks. You can also just use this to generalize networks, which means can I generate new networks that look statistically similar to an old network? You fit the model to the network, and then you run the model forward and use it to generate a network from the model. You can produce another network which is not the same as the one you saw, but is statistically similar to it, which is a trick that a lot of people are very interested in, for instance, in the internet community. They're very interested in ways of generating networks that look like the internet but are not the internet. Sorry? Topology generators is what they call them, exactly, yeah. So you can use models like this to do that. Latent-space structure is sort of another generalization of community structure where instead of belonging to discrete communities, everybody just has a position in some space. And then the probability of connection between two nodes depends on those positions in space. This can be used, for instance, to embed networks in a physical space to make an estimate of where the nodes live in the physical space. So this is related to what they call graph-on models, which I guess some people here are well familiar with. You give each node a position in the space X, and then you have some function here, which are called omega of X and Y, which says the probability that there is an edge between a node at position X and a node at position Y. Probability density, I guess, technically. So it turns out to be tricky to fit these things to observe data. The way we did it was we imposed some smoothness on this probability function by expanding it in a set of basis functions, then truncating that expansion at some finite order n. Doesn't really matter what basis functions you used. Any polynomial complete set of non-negative basis functions will do. We used Bernstein polynomials, but you could probably use some kernel density functions or something like that. It probably work just as well.
So you decided to use a one-dimensional?
This is just one-dimensional. Absolutely, yeah. You could do it in higher dimensions in principle, but this is just a one-dimensional case. It turns out that the Bernstein polynomials are nice because they give a very elegant EM algorithm in this case. You can write out the EM algorithm. You can run this on various networks. Here's us running it on the motorways in the United States. So we just gave it the topology of the network. We didn't give it the map. And it colors in the nodes depending on where it thinks they live in a one-dimensional space. And it's clearly found a dimension that runs from sort of the northeast of the country across to the west coast, like that. So it's understood that there is a spatial element to this network, even though we didn't tell it that, we only gave it the topology. Here's this is a neural network of C. elegans, a little worm about this long. It's the only organism whose neural network's wiring is completely known from beginning to end. We didn't tell it the positions of the neurons, we only told it the wiring, and again the colors correspond to where it thinks the neurons live. It's done a pretty good job of embedding them in the appropriate space. Okay, finally, one last example and then I'll finish. So one thing that we applied this spatial embedding to is ranking in social networks. So this is not actually spatial now. So we were interested in, we had these data on friendship networks among school children in the US. They're directed networks now. And one of the interesting things you find in these networks is that so why are they directed networks? They're directed because how do you determine who's friends with whom? You just ask them. And person A says, I'm friends with person B. Right, that's the unit. So there's a directed connection from A to B. The interesting thing about these networks is a lot of the time, about 50% of the time, B doesn't say they're friends with A. Right? The connection only goes one way. What are you supposed to make of that? Well, many people say you should just ignore it. I mean, I think the majority of the literature is, we'll just ignore the directions, throw them away, treat it as an undirected network. Our hypothesis was that actually there's some information there in these directions. The hypothesis is that there's some sort of rank or status amongst these school kids, and the cool kids are much less likely to say they're friends with the uncool kids than vice versa. So that if you look at the directed edges, you should be able to infer the ranking from them. So there's a one-dimensional space here, which is sort of coolness in schools, and the claim is that by doing this kind of spatial embedding latent space inference, we should be able to work out who's cool in school. Right? So we have the actual data, and we did the fit. So you find sort of interesting thing. For the two-way edges, the one where both, so you infer this ranking, right? What we've done is we've assigned all the kids to this one-dimensional space, cool at the top, uncool at the bottom. And for the edges that go both ways, both kids say they're friends with each other. Turns out their ranks are very closely equal. The delta, that's what this plot here is showing, it's showing the difference in ranks. The delta is very close to zero, so you get this big spike at zero. In other words, pairs of school students who really are friends tend to be very closely similar in this inferred coolness index. They know how cool they are, and they're friends with other people who are as cool as they are. The ones that only go one way, there's also a big spike at zero. Right? So many of these may actually be real friendships, but there's always this sort of tail that goes off to the right. That's people saying they're friends with people who are cooler than they are by our measure. And it's sort of interesting, it sort of drops off a bit there. It's like people say that they're friends with people who are just a bit cooler than they are, but not a lot cooler. Like, you don't say you're friends with the coolest kid in the class because nobody's going to believe you. But if you say you're friends with a person who's just a little bit cooler than you, then maybe not big. Right? So you can check this against things like, for example,
tail the other way too, right?
Sorry?
There's quite a bit of a tail the other way.
There is a little bit of a tail the other way, it's true. Right, yeah.
Unawareness.
So, yeah, there is a little bit of that. That's certainly true. You can check this against things like total injury. How many people said they were friends with you? In other words, your total popularity. And there's a strong correlation there. So our sort of coolness index correlates strongly with total popularity. Okay, that looks promising. You can also check it against age, for example, grade, year in school, and it's well known, sociologists believe that older kids have a lot more status in school than younger kids. So you see that this coolness index goes up.
Does it go the other way in retirement?
Does it go the other way?
In retirement homes.
It's a good question. I don't know the answer. And finally, here's just one picture of one of the networks in the schools with the color representing grades. And well, it's a little bit difficult to see, but the claim is that sort of most of the edges here point up. Here, the vertical axis is this rank, this coolness that we gave them. The oldest kids are the coolest, and the youngest kids are the least cool. Okay, so I will stop talking now. Before I do, let me just say thank you to my terrific collaborators, a bunch of students and former students in my group at Michigan, to postdocs, both of them now not postdocs anymore. Aaron's at UC Boulder, and Tiago is just about to start at the University of Bath in the master department there. And two faculty collaborators, Elizabeth Brooke and Chris Moore, and that's it. I'm done. Thank you. And sorry again for the cluelessness about where this talk started.
So you're also rather some sociologists want to make a test of scientific collaboration, not by measure of publication, but asking about unpublished collaborations and see whether you have the same type of coolness factor there.
Right. So that's an interesting point. So there have been some studies of that where people have looked at acknowledgements, you know, in the acknowledgements in the paper. Thank you to so-and-so for useful conversations. The catch is that, of course, it's much more laborious to compile that data than it is just stuff about co-authorship, which you can get directly from databases, like, you know, Medline or whatever. So they tend to have been rather small studies, and I don't know of any publicly available data sets, but that's actually a really nice idea. I've been not at all surprised to learn that's true. People tend to acknowledge a useful conversation with, you know, a Nobel laureate or something like that, much more than a Nobel laureate is like to acknowledge a conversation with that. That would be interesting to look at. Yeah. Yes?
So about this setting where you put probabilities instead of edges and edge. So I don't know if you know the generalized exponential random graph models where they have weighted the same question. So what are the assumptions that they have that you don't have?
So the assumptions are that you have to have a process that generates the weights, right? So it's now not just a question of is there an edge here or is there not an edge here. Once you generate an edge, you also have to decide what weight it
So you
has.
want to estimate the weight. You observe a network, a weighted network,
Right.
and you want to estimate the weights, which are basically...
No. Typically, what you want to estimate are some hidden variables. So you observe the weights, and you want to estimate some hidden variables, you know, like group memberships or something like that, or in exponential random graphs, they're typically the coefficients of small clusters in the network, you know, 2 stars or something, or triangles or something. And you do that by fitting the observed network and its weights to this generative process that creates networks and weights. So so it doesn't give you weights, you're using the weights as input data, but in order to do that, you have to have some hypothesis about the process by which those weights are generated. And in most cases, that's missing. In most cases, we don't really know what that would be. Yeah.
And just a similar question. So if you have a binary network, in principle, you can estimate PIJs and use them as what you do.
PIJs.
So probability of an edge being present. You can estimate those. Fixing certain
the things that I was calling the omegas.
Yeah.
Right, absolutely, yes, you can. So in most cases, people haven't actually shown much interest in what the edge probabilities are. So they're treated as just as kind of nuisance parameters.
Yeah, but I mean, in principle, you can apply this model on every network. Your network doesn't have to be of that specific form. If you observe a binary network, you can do this trick to apply the other model.
Oh, I see. The stuff with the probabilities?
Yeah.
Yes, absolutely. There's no reason why that has to be the stochastic block model that goes in there. That sort of probability of A, the unobserved adjacency matrix, could be any parameterized form.
But in principle, your probabilities are some sort of estimated probabilities. They're simply proportions. The probabilities that you had in your genetic
The probabilities of the unobserved networks,
yeah.
you mean? Yes, absolutely. They're just some parameterized
Kind
form.
of estimated
I happen to
as well.
use one particular one, but lots of others would be possible. Yeah, the basic framework would work for any kind of
Binary.
uncertain data on, you know, with any kind of underlying assumption. I mean, in actual fact, you wouldn't use the stochastic block model because it works terribly for most real networks. You'd use a degree-corrected version or an overlapping version or a mixed membership model, something like that. Something that works better.
More question for Professor Newman? I have one more question. So I really like your analogy, the analogy you gave at the beginning of the talk, saying like you could use the stochastic block model like a straight line approximating a pattern of dots. So, but let's say if my pattern of dots look like a circle, then fitting a straight line would be the worst thing to do.
Absolutely.
So following that line, like what would be alternatives of this stochastic block model that we could use as a first order approximation of your thoughts?
Yeah, so this is a good question, and this, for me, is one of the miraculous things about this stuff. It's very clear that these models that we're looking at are wrong, and they're blatantly wrong in some really, really bad ways, and yet when you fit them, you still get useful information out of the fits. So this is not just true about networks, this is true about the whole of modern statistics, basically. All models are wrong, right? But somehow we managed to get useful information out of fitting them, and it's a bit of a mystery to me why this is. You might say, well, it's just you have to make your model sufficiently complex somehow in order to capture the structure in your network. But this is clearly not true, because you look at something like the stochastic block model, and it actually doesn't work. And the reason it doesn't work is because it doesn't capture the broad degree distributions that most of these networks have. So there's something called the degree-corrected stochastic block model, which does do that. So you add in this one extra element, and now it works beautifully. And yet, that degree-corrected model is still a really bad model. So what you're doing is you're comparing a really bad model against another very slightly better model, which is still really bad, and yet this bad one works and this really bad one doesn't. So it's not like the line is between good model and bad model. The line is between bad model and really bad model. So it's very much a mystery to me where you put the line, right? They're all bad models. So you're absolutely right. Your analogy is very nice. It's fitting the ordinary stochastic block model is like fitting a straight line through a curved bunch of data.
And
You can do the fit.
is a parabola.
Exactly. You can do the fit. There is a best fit, but even the best fit is terrible, right? Because the model just doesn't fit the data. And then you do this degree correction thing, and then somehow now it kind of fits quite nicely. And it's, I find, yeah, it's a mystery why this works. As I say, it's not just a mystery about networks. This is kind of applies to all of statistics. We get good answers out of bad models. That's not the mystery. It's, you know, it's how bad do they have to be before we stop getting good answers out of them? And I don't know the answer. All right, very good.